First of all, I would like to thank the board and also the organizers of this conference for giving me this opportunity to present my paper, which is about fatigue life prediction of ABS graphene nanoplatelets, 3D printed nanocomposite part. So here is the contents. I'll start with a brief introduction about the topic and then a brief literature review. Then I'll talk a little bit about the methodology, experiments, life predictions, results, and finally conclusions. So additive manufacturing, also known as 3D printing or rapid prototyping, is a manufacturing technique that can be used for fabricating different components like metals, alloys, plastics, or composites. It has some advantages over traditional techniques such as low cost, rapid processing, and ability to produce complex geometries. And at the same time, it has some disadvantages such as anisotropy or lack of reliability that hinders manufacturers to use this technique in sensitive applications. AM categories can be categorized as photopolymerization, powder-based printing, lamination, or material extrusion. Our focus in this study is on material extrusion. So fused deposition modeling, or FDM process, is an extrusion-based technique in which a raw material as a filament passes through a nozzle. Its temperature rises above its melting point, and it is laid on a hot bed layer by layer to form a desired shape. It has some process parameters such as building direction, raster orientation, field density, printing velocity, nozzle diameter, nozzle temperature, and layer thickness. In this study, we have considered raster orientation and adding nanofillers. It has been proven that addition of nanofillers not only enhance the mechanical properties, but it can also give more functionality to it. So here is the literature review. Actually, there are numerous methods for predicting fatigue life of additively manufactured components. I'm not going into the details of each of them, but in summary, we can say that SN curve approach, critical distance theory for components with notch, and fracture mechanics-based approaches, critical plane approach for multi-axial stress condition, and machine learning approaches are most commonly used techniques. The methodology, here we can see that there are some discontinuities between the filaments of a FDM process sample. The idea of this study comes from this fact that these discontinuities between the filaments can act like a sharp notch, and this notch can reduce the fatigue life of the component substantially. So we start with sample preparation. Then we do some fatigue testing on neat material as filaments and 3D printed samples. From the fatigue test data of filaments, we can extract material constants like fatigue parameters, strain-based fatigue parameters, and using fatigue data of filament and 3D printed samples, we will be able to find fatigue strength reduction factors. And then we can analyze stress and strain in the notch sample using both Romberg-Osgood and Neuber equation. And then after that, we will be able to determine life using modified Morrow or Smith-Wasson-Tauber model. Here is the experiments. We used ABS as a matrix and graphene nanoplatelets as the filler. Also, we used the combined solvent mixing and melting compounding to fabricate our filaments and then 3D printed samples. We varied graphene nanoplatelets at 0.1, 0.5, and 1% graphene nanoplatelets. And also we consider two different raster orientations as 0 and 90 degrees. Here we can see the results of stress strain curves and also the SN curves. We can see that adding 0.1 and 0.5% GNP can give us the highest tensile strength, while adding 1% GNPs, we can see that there is no major impact on tensile strength. From this stress strain curve, we will be able to find Romberg-Osgood parameters. And then for the SN curve, we can see that adding 0.5% GNP can give us the highest fatigue life, and adding 1% GNP, the lowest fatigue life. Using those data for SN curve, we can determine the strain-based fatigue parameters. So here we can see the fatigue life of 3D printed parts at 0 and 90 degree raster orientation. Samples with 0 degree raster orientations experienced highest fatigue life, while samples with 90 degree raster orientation possessed lowest fatigue life. Also, we can see that adding 0.5% and 1% GNP, especially in high cycle fatigue, experience highest fatigue life for both raster angles. In this slide, we can see that we have used these SN data to obtain strain-based fatigue parameters. And the data has been summarized in this table. We have used these data along with the Romberg-Osgood and Neuber equation to obtain fatigue strength reduction factors. And all these data have been used to predict the fatigue life. So here we can see that the fatigue life of filaments are much higher than fatigue life of 3D printed samples. That's why we have considered that this sample, the 3D printed sample, can be considered as a homogeneous material, but with a notch. So we have calculated the notch strength reduction factors for all these load levels, and the results have been summarized in this table. And then, so here we can see the material degradation during cyclic loads. Material degradation had substantial effect on fatigue life. As we can see, with the progress of cycles, the Young modulus reduced roughly about 5% to 15%, depending on the concentration of GNPs. So this reduced Young modulus has been used in Romberg-Osgood equation and Neuber's equation. with solving two sets of these equations, we will be able to find both mean stress and strain amplitude. And then we have used modified Morrow's damage equation and the Smith-Watson-Topper equation to predict fatigue lives. Here we can see the results. As we can see, both models over slightly, for example, the Smith-Watson-Topper slightly over predicted the results, but the modified Morrow's damage equation over predicted the results largely. So, but the results for Smith-Watson-Topper, the majority of the data fell in between two scatter bands with the factor of plus and minus 2. To conclude, the proposed method is an effective technique for predicting fatigue life of notched 3D printed samples. Material degradation, specifically Young's modulus during cyclic tests, had a substantial effect on fatigue life. And overall, both modified Morrow's damage model and the Smith-Watson model over-predicted the fatigue lives. This is because the models unable to consider the internal porosity and defects in the samples. And finally, the majority of data predicted using a Smith-Watson-Topper model fell in between scattered bonds with factor of plus and minus 2. However, modified Morrow's damage equation over-predicted fatigue lives. Thank you.